In this section, we're applying the methods of optimization to geometric problems. In number 1, find the length and width of a rectangle that has a perimeter of 100 meters and a maximum area. I've outlined the steps above, and I'll number the steps within the problems as I work through. So, step 1 says to write the primary equation for the quantity to be optimized, either maximized or minimized, and here it says to maximize the area. So the formula for area of a rectangle is going to be length times width. So it's got two sides, length and length the same, and then two other sides, the width and width the same. Now it also tells me the perimeter is 100 meters, so that's where your secondary equation is going to come in as helpful. So perimeter is going to be the distance around. So I've got two lengths and two widths, and I know that that's equal to 100. So this known constant is what's going to allow me to get a substitution so that I can get a single variable over here. Because when we're differentiating, remember when we are trying to optimize, we have to take the derivative to find the critical numbers. We need a single variable over here. We can't have two different variables. So we need to solve this equation for either L or W to get a substitution over here. And it doesn't matter which one you solve for. So I'm just going to choose to solve this secondary equation for L. So 2L plus 2W is 100. To solve for L, I'm going to subtract this 2W. That's going to give me 2L is equal to 100 minus 2W. And if I divide both sides by 2, remember that divides each term by 2, that tells me L is 50 minus W. So I can take the substitution of 50 minus W and put it in place of L. Now A is going to be in terms of just one variable, W. So I've got 50 minus W for L times W, and I can go ahead and distribute that W so I don't have to use a product rule. So I've got that A is 50W minus W squared. So now that's just A, that's not its derivative. So trying to optimize, trying to maximize, we need A's critical numbers. So this all through here, the solving for one variable in the secondary equation, plugging it into the primary equation, that's what I numbered as step 3 in the above steps. Step 4 is where the calculus comes in. You're looking at your primary equation now in terms of one variable, and you want to find the critical numbers. Now we're looking at A prime. The derivative of 50W with respect to W is 50. The derivative of negative W squared is going to be 2W. And now to find the critical numbers, since that's a polynomial, I only need to worry about the equals 0 case. I'm going to add the 2W over, divide by 2, and that's going to give me that W is equal to 25. Now, I'm not completely done because I need to go ahead and find, or I need to go ahead and be sure that this does the job of doing the maximizing. So this is where your analysis with the second derivative test comes in. And I'm sorry if you hear background noise. This class changed time, so out in the hallway it gets a little noisy. So A double prime is going to equal the derivative of 50, of course, a constant is 0, and negative 2W, the derivative is negative 2. So this is always going to be negative. So certainly, if I plug in any constant, it's going to be a negative result. So that means that A is going to be concave down. So this function A is going to be concave down. So it definitely would produce a maximum. So step 6 is to go back and find your other dimension. Now we can go back to this formula, the secondary equation, but we've already solved that for the variable that we actually need to figure out now. So let's take this formula here. L is equal to 50 minus W, and we know that W is 25. And we can figure out that L, of course, is 25. So the dimensions that will maximize the area, and since perimeter was in terms of meters, I can say that the width is 25 meters and the length is also 25 meters. So those are not always going to be the same measurement. It just turned out that way in this problem. Number 2. So we're looking again at a rectangle with length and width, but this time we're looking at the opposite situation. So we're given the area in square feet, and we're asked to minimize perimeter. Now, our equations are going to trade places, because if we're asked to minimize perimeter, that's now my primary equation. And if we're given the area, that's now my secondary equation. And we know that that's equal to 169 square feet. So I do the same type of thing. I solve my secondary equation for one of the variables, and I'll be consistent like I did with the other one and solve for L. So I can just divide by W. And now I've got a substitution that I can put in place of L in the primary equation. So P is equal to 2 times 169 over W plus 2W, which is equal to 2 times 169, you may need to grab your calculators, 338 plus 2W. So in order to differentiate, we need to have that W up top. And now it's in a form that we can go ahead and take the derivative. So all of this, remember, here and here is going to be your step 3 work. So step 4 is to go ahead and differentiate what it is we're trying to optimize. And here we're trying to minimize perimeter. So we need P prime. And we can take it from this stage here. So the derivative of 338 W to the negative 1, we power down. And then this term is linear, so its derivative is just the constant. And we need to be careful here because we have a negative exponent. So we're going to rewrite this as negative 338 using a positive exponent over W squared and then plus 2. And the way I've showed you guys in the video before is to get a common denominator, so I'll be consistent with that. So we'll multiply by W squared over W squared. And remember, we don't have to worry about the case of W equals 0 because this has an implied domain that width and length have to be greater than 0. So we're really only worrying about the equals 0 case. So W equals 0 is not going to be of concern because it can't be 0 or we don't have a rectangle. So we're really only worried about the P prime equals 0 case. So we can go ahead and add that 338 over. And we can divide by 2. So we know that that's going to be 169. And then we can square root both sides. And normally we use plus or minus, but here we know we don't have negative width, so we're just going to use the positive. And the square root of 169 is 13. So if you've got your width, you can do your analysis now with step 5. So you're going to use your second derivative test. We need P double prime. So I would pick up from this step here. You're going to be taking the negative 2 down. So you've got negative. So it's going to be negative times negative, which is a positive. So I'm just going to work with the positive numbers here. So times 2. So that's going to be a positive 676, and you're subtracting 1. And remember, if you're doing anything with the derivative, you need to rewrite with positive exponents. So you've got a positive number on the top, and you're going to be plugging in a positive number and cubing it in the bottom. Well, certainly that's going to be positive. So if you plug in 13 into the second derivative, that is going to be greater than 0. So greater than 0 would tell me that P is going to be concave up, which would produce a minimum. And that is my goal here. I'm trying to get a minimum parameter for P. So step 6 is to find the missing other variable, and we solved for that other variable in step 2. L is 169 over W. So let's go ahead and plug in our W. And more noise out in the hallway. I apologize again. out of my control. So 169 over 13 is equal to 13. So final answer here, in order to minimize perimeter, we would want that the width is equal to 13, and this time, since the known amount was given in square feet, it's going to be feet, and the length is going to be 13 feet as well.